Hey, so welcome to this week's edition of our GReTA seminar. It's the third one this year already, so the year is moving on. It's my pleasure to welcome Steffen, Zschaler, and Alexander Burdusel today. So I found out, well, I knew before, but I just confirmed that again, that Steffen actually studied in Dresden originally, at least did his PhD there, which is nice because I started studying informatics there as well. Many years ago, 98 to 98, no, 89 to 91.
That was just before me then.
Yeah, before they moved, before I moved to Berlin to the Technical University. And he's been sort of obviously studying there, doing his PhD, and then he moved to Lancaster, and from Lancaster to King's College London, where he is now. And he's an expert in model-driven development and leads the MDE network in the UK as well. And he brought a bit of support on the technical side, if I may say so. So Alexandru is a PhD student at King's College, or I mean, maybe just at the end of his PhD after this Viva. And he will be providing, yeah, as I said, maybe some of the details. So we have both the big picture and strategy and the sort of detailed technical expertise here. So what can go wrong? So please, Steffen and Alexandru, your stage.
Thank you, Raiko. Slightly scary when somebody says, "What can possibly go wrong?" That's always a bad start. I find.
Not superstitious.
Fingers crossed. Yes, thank you for inviting the talk as well. Yes, I just noticed that I've mistyped Alexandru's name. It should be Alexandru Burdusel on the slides, who's here with us. Yes, and he's sort of the PhD student who's done a lot of the work that I'm going to be talking about in the time-honored tradition of academia. And so if there are more technical questions, I might suddenly then point at him and go, "You take that one," and be silent. What I want to do is I want to talk about our MDEOptimiser tool, which is about optimization, search-based optimization over models in the world of sort of EMF, which is sort of the model-driven engineering world, I guess. And the link to GReTA, which obviously is about graph transformations, is that we use a lot of Henshin graph transformation as part of that optimization and search process. And I'm going to try and talk a little bit about what that allows us to do and how that allows us to approach some of the interesting problems in that sort of space, and also where we might be going in the future, hopefully. A lot of the work that I'm going to talk about, obviously, has been done quite substantially by Alexandru and myself, but also with a lot of other collaborators, which you'll see occasionally in sort of the paper authorships. And I've seen that quite a few of them are actually on the call as well today. Sorry, guys, you know this stuff already, but hopefully you'll recognize it and don't feel that I'm misrepresenting it. So let's jump right in here. So this is in the space of sort of optimization problems. Optimization obviously is a pervasive problem everywhere, and typically it's originally sort of been approached from a sort of very mathematical perspective, right? Where and also encoded in a very mathematical way, using a set of constraints for a solution, a set of sort of control variables, things that we can change. And in the mathematical encoding, they're typically literally variables that can sort of take numbers or elements from sets. And then objective functions, either just one or possibly more than one, which basically, given a set of values for these control variables, tell us how good that potential solution is, right? And so we can compare the values of these objective functions for different assignments of values to the control variables, and that gives us sort of a ranking, the possibility to rank and compare these different solutions in terms of their quality. We're interested in this initially in the context of sort of more software engineering, where there are a lot of problems that are search-based or optimization problems, really, right? Things like refactoring architectures or just class designs, etc. improving processes, making decisions about, what to focus on when, deploying components on servers, on physical machines, so in a virtualization space and a cloud space, figuring out what to run where and which machines to spin up and which machines to spin down, and how that affects your energy consumption and your cost versus your performance and responsiveness. Program repair is something that sort of the search-based software engineering people, I think, have focused on a fair amount, trying to basically fix bugs out automatically by trying to optimize the number of tests that a program satisfies or completes successfully. These are all sort of examples of sort of optimization problems as sort of maybe an indication of why this is interesting from a software engineering perspective. The general structure of these, and what I'm going to do, there's a lot of optimization techniques out there, but a lot of the time in this talk, I'm actually going to focus on search-based approaches to optimization. And the general structure of these sort of approaches is that we start with a solution, and then we sort of iterate over that solution and make small changes to it, and at every step evaluate the quality of the solutions that we now have, and decide which ones to keep, which ones to explore further, and in which direction to continue exploring, until we sort of decide that we've done enough, which could either be because we've set ourselves a certain amount of time that we want to do this for, or the quality really doesn't improve anymore, we don't seem to be finding better solutions, or things like that, right? Generally, this is useful in problems where there is a search space that's too large to be efficiently enumerated completely, right? I mean, if I just can enumerate the 15 or 20 solutions, potential solutions in there, and look at each one of them in turn, then that's the sensible thing to do, because that guarantees me that I will find the best one. But for these problems, we're talking about spaces that are sort of in the thousands and 10,000s and millions of potential solutions, where eventually it becomes really difficult to just enumerate things, and we need a more efficient way of searching this space. And that's where this approach that's sort of guided through these sort of fitness functions and uses them to decide which direction to go next is helpful. Doing this, however, is actually not simple. Okay, so in order to successfully apply sort of a search-based approach to your problem, you've got to know a fair amount about optimization. And the SBSE community has sort of been eating out on this for a long time, and lots of people have written a PhD about solving one search-based software engineering problem and building the search approach for that problem and figuring it all out, working that all out. And there's nothing wrong with that, but of course, for sort of the working software engineer, it's a little bit impractical to expect that you've got to invest 3 years of your time to solve that one problem, when actually, you've got 10 of those to solve. And so what we've been trying to do, what we've been working towards, is to try and sort of use MD approaches, model-driven engineering approaches, to try and make that a little bit simpler, and to try and capture some of that optimization expertise in a way where we can hopefully apply it slightly more easily. And so the idea here is that we go back to this top level picture where we say we've got a domain expert who knows what the problem that they want to solve, right? Say a software engineer knows the design problem that they want to solve, and we have the optimization tool that sort of knows how to do optimizations. And what we are hoping to try to achieve is to move the optimization knowledge, so the knowledge about how to do optimizations well, from the user into the tool, so that the tool becomes more intelligent about doing these things, and the user, ideally, in an ideal world, only has to describe the problem, and from there we can get to doing an efficient search or an efficient optimization. Now, this is sort of the vision statement. Really, it's not where we are at the moment, but it's sort of it's me trying to set the context what comes. So if in order to do this, what's the idea? The idea is that what we want from our user is a description of the search space using technology that we have already for people to for domain experts to describe their problems. And the key technology here is domain-specific modeling languages. So modeling languages that have been developed for a particular problem domain, and we want to be able to reuse those languages that already exist for some problem domains, or that we could, or where we know how to develop these languages for other problem domains. We want to be able to reuse that technique and that approach for people to just say, this is the sort of problem I want to solve. Okay, so the DSML essentially gives us the search space. It says a model in that DSML potentially is a solution to my problem. Okay, there may be what we need to say then is we need to say, if you give me a problem, an example model, essentially, what are the parts of that are fixed, that you can't change, that you can't do anything about, and what are the parts that you can change? That goes back to the sort of idea of the control variables in the sort of more mathematical encoding of an optimization problem, right? So we need to be able to say, this part of the DSML is the bit that we actually want to change, and everything else just is context information describing the problem that we're trying to solve here. Okay. There may be some additional constraints. So sometimes it may be the case that we say not every instance of this DSML is actually a valid solution. It may be that there are some other context constraints that we can't capture in the model. So we may need to provide some of those. And obviously we need to provide objective functions. And I'm going to say a little bit in a moment about what these objective functions look like. But again, we want this to be all tied together in this world where we're talking about DSMLs and about models. So in the terminology that our domain expert already knows, right? Ideally, we don't want them to have to step too far away from that. And then the other thing we need to say, well, this is sort of our general search space, but now what's the specific problem that we're trying to solve? And we want to provide that. We provide a specific model that's expressed in this DSML. And we say that's sort of our starting point for our optimization problem. This is the information that we have. And it may be an incomplete model, right? So it may be missing some connections, and the goal of the search may be to figure out what the right connections are, for example. And from this, what we want to do is we want to automatically get to a point that finds us the optimal solution by encoding the problem in an appropriate way, applying an appropriate optimization algorithm, and then finding optimal solutions, which are again expressed as instances of our DSML. Okay, so I'm being a little bit hand wavy here on purpose, okay, in not telling you at this point what the encoding is and what the appropriate optimization algorithm is, because in the sort of longer term vision, the idea really is to be able, ideally, to get to a point where we can analyze the problem that we're given, and we can choose between different optimization algorithms and pick the one that would be most efficient at solving this. And obviously different algorithms may require different encodings. Again, that's not quite where we are at the moment. I'm going to talk about where we are at the moment in a moment. What am I missing here? Oh, yes. Now, what we're actually doing at the moment in MDEOptimiser is we've essentially chosen one particular optimization algorithm, okay? And that algorithm is a version of evolutionary search. So that's an algorithm that will actually make incremental modifications to the initial solution, check the fitness functions at each state, and then decide in which direction to continue searching. So there are two things that we do here. One is that we actually use the models directly as the problem encoding. So we do not take the approach that maybe many sort of genetic algorithms use, that we sort of create a somewhat artificial, maybe bit vector or integer vector encoding of our models. People have tried this. We found that for models and for graph structures like these models in general, that's actually not a particularly promising direction, because it becomes really, really difficult to construct an efficient, often becomes really difficult to construct an efficient encoding of the model information that's locality preserving as we make changes to it, as we change things in the bit vector. And so it becomes actually really expensive to make these changes and make the search efficient. So we use the model directly as our encoding. And then, as I said, we use an evolutionary search over these models. So we make changes to the models as we go along. Okay. And so let's just look back at our picture from before. So what we actually do is with that input, that description of the problem, we basically split into these three parts. We have the solution meta model, our DSL, and we have possibly a set of additional constraints, which sort of say, this is what solutions look like. This is our search space. We provide a set of fitness functions. I'm going to say what they look like in a moment. And then we need to talk about how solutions can be derived, right? So we need to tell the machinery, how do I go from one solution to the next? Okay. And this is what this looks like. So for the search operators, for telling the engine how we go from one solution to the next, we use graph transformations because seems the appropriate thing to do. We've got models which are graph structures, and we want to say, if I have one model, how do I produce a variation of that model for my next search step? And that's a task that graph transformations are really good at. And in particular, we use Henshin because we're working in this sort of EMF space for describing our models. And Henshin obviously is a very suitable tool in that context. For the fitness functions, we can then again use technology that already exists by just writing queries over our models, right? A fitness function in the easiest case just becomes a query we can express in something like OCL, the object constraint language. But you can also write a bit of Java code, which just, again, queries the model. Or if you want to, you can write a bit of Java code that takes the model information and runs a simulation for a little bit, comes back with a simulation result, and uses that as the fitness value, which can be quite powerful, but obviously becomes a little slow over the longer run because you're going to call those fitness functions a lot over the course of a search. And then with these sort of inputs, we go into the general evolutionary search algorithm where we create a population. So we typically we are using an NSGA2 for our algorithm, so a population-based algorithm, and we create an initial population by starting from our one start model, from our one problem model, and basically applying some random mutations, some random graph transformation steps from the set of graph transformation rules that we've been given to that. And that gives us a population. And then we iterate over that by generating new candidates using the graph transformation rules that we've been given, evaluating the fitness using the queries that we've been given, deciding what the new round population should be, and rinsing and repeating the whole thing until we decide that we're done. And typically we decide that we're done based on either a time box that we say we're going to let this run for so and so many seconds or minutes, a number of evaluations, a number of evolutions that we let it to run, or, as I said, because the quality hasn't changed over a number of iterations. And then the result is that we get a population of model specs. So we don't have to do any back translation or anything like that. We don't have to do, the genotype, phenotype kind of translations that you see in genetic algorithms. We just have the product right there. We get that set of models back, and we can then look at those and pick the right one for us. So here's what that looks like in the MDEOptimiser tool. This is how you describe a search problem in these 4 parts here at the top. It's not, you don't have to read this in detail. It's just sort of to give you an indication. At the top, we describe the actual problem, and that consists of the meta model. And this is just a link to a standard meta model file here, and the start model. And again, that just links out to the file where that model is. Then we specify the fitness functions, and in our tool, we provide 2 options. You can either write some OCL directly in here, or more typically what we tend to do is we just link to a Java class, and I'm going to show you one of the example classes here in a moment. And then we link to a set of Henshin transformation units. Typically we use rules, but I think we've played with some units in some more complex units in some other examples as well, which defines the set of mutation operators, the set of change steps that you can apply. And then there's a little bit of configuration down here, which we'd rather not have, but at the moment I can't quite get rid of yet. And then obviously that comes with extra files that have all that extra information that you reference from this one central place. And so here I'm showing you an example of this for one particular case study, which is about refactoring class diagrams. So on the top left, we can see the meta model for this problem, where we say, well, okay, we have these entities which contain properties or attributes, if you want, which may have a type. And there can be a generalization relationship between those entities. So entities are essentially classes, right? And then the job is, to apply a number of refactorings in order to optimize that sort of hierarchy of entities and properties. And the types of refactorings that you can apply are pulling up attributes. If all the subclasses of a class all have the same attribute in them, then you can just pull that up into the superclass and remove it from the subclasses, for example. I think here we're actually creating such, in this rule down here that you can see at the bottom here, we're actually creating such a class, intermediary class, to sort of say there's a subset of classes here that share the same property. Let's create a new superclass for them and pull up the attribute so that we can pull up the attribute into theirs. So that these operators for this refactoring case study actually become quite involved, right? It's quite complex. But the beauty of that is, because we have this graph transformation power, we can actually express exactly what makes for a legal change to our model, which again is more powerful than what you can typically do in sort of genetic algorithm-based approaches, where you typically will use sort of a fairly generic operator that just flips a bit or changes the value of one of the elements of an integer vector or something like that, and then you kind of hope for the best. Here we can describe fairly complex operators to make sure that we only make valid changes, legal changes. And then on the top right, you see a Java class, an example of a fitness function implementation. And it's literally just, they have to implement this iGuidance function interface here, which essentially has this compute fitness operation that takes in a solution and produces and returns a number. And what they do here is we look at the model that's contained in the solution, and we count the number of property objects in there, and we count the number of entity objects, and we sum that up. We give the entities a little higher weight than the properties in this case. And this is going to be used in a minimization objective. So we're going to say, we want as few as possible of those. And that means if we have a lot of subclasses that all have the same property, and we can kick out all of those properties and just create a single property object in the superclass, then that fitness function will become better, and the search will be guided in that direction, right? And to sort of consider that as a sensible direction. Now, I said already that we're using these graph transformations for the search. And before I talk a little bit about why that's sometimes painful, but where also the fact that we're using graph transformations can help us in that regard, I want to just have a brief detour to sort of talk about a different way of thinking about this general search problem here. Okay, so I've said that we're using the models themselves as the encodings for our search, and we then apply evolutionary search over models. Actually, there's an alternative way of thinking about this, right? So this is sort of saying we're searching for the optimal model. Starting from a start model, we're searching for the optimal model, and that's what we want. You can alternatively, of course, also think about this as saying, no, we're searching for the optimal transformation, the optimal chain of transformation applications from that start model to some target model. Okay. Again, the fitness functions are still fitness functions over the actual models, but you can think about this as, rather than searching for models, you search for transformations, and then you encode your solutions not as the model, as the final model, but you encode your solutions as a sequence of transformation applications. And there are other tools out there that do that. Things like tools like Momoti from Manuel Wimmer's group, and Viatra DSE, for example, from Daniel Varro's group. They essentially do this sort of thing, right? They search over these sequences of transformations. And so one interesting question that we asked ourselves was, does it matter whether you search for the optimal model or whether you search for the optimal transformation. And I'm going to do the marketing-y thing now and say, yes, it does. And searching for models is better. We wrote a paper about this that sort of says that, but obviously, you know, strictly speaking, I think the jury is still out a little bit. But at least for the case studies that we looked at, for the examples that we looked at, our experiments suggested that as the problems grow larger, the approach that searches for optimal models and uses the models as the encoding seems to have the edge. So you can see this in these diagrams here. Let me perhaps briefly tell you how to read the diagrams first. So the diagrams on the x-axis show the number of evolutions, and on the y-axis they show something called the hypervolume. The hypervolume is an indication for multi-objective optimization problems. So where we have more than one objective function, the hypervolume is a generalized indication of how good our solution is. And you can think of it as telling you how close to the perfect optimal solution have we got with the set of solutions that we found. Okay, higher values are better than lower values for the hypervolumes. And so you can see here what we've done is we've basically shown as the search progresses through these evolutions, and evolution is where we take the entire population, we make decisions about which solutions to mutate, and we make a decision about what the new population will be, right? That's an evolution essentially. And as the search progresses over those evolutions, what you can see here is how the hypervolume changes over time. And you want to see lines that sort of are reasonably monotonic. If they're not monotonic, then typically something strange is going on in your search, right? Because you tend to keep the good solutions that you found in the past. And on the top here, it might be a little bit difficult to see this sort of purplish line here and the purplish line here. That's our MDEOptimiser tool. The other tool lines are two slight variations of the MomoT tool. And the reason why we've compared these two tools is because on the technological side, they're essentially using the same technologies. They're both using EMF, they're both using Henshin. So we could use the exact same models, the exact same transformation rules, etc., to compare things. And as you can see, you know, for this model here, which is still relatively small, and the refactoring case for this model, where it's still relatively small, we're not doing quite so brilliantly. But as we go to these bigger models, where we also need more evolutions to get somewhere sensible, we can see that while we don't necessarily find better solutions overall than MomoT was able to find, we find them faster, which is a good thing already. If we look at the CRA case down here, we can actually see their MDEOptimiser is the sort of cyan greenish sort of curve here, right? We can see that actually, again, for the really small models, we're not doing totally brilliantly, but we're not doing completely rubbish either. But as the size of the model grows, it becomes more and more the case that the model-based encoding becomes more efficient than the transformation-based encoding. All the details are in the paper listed here, of course. So this was encouraging, obviously, to us to sort of suggest that this approach is sensible. This is worth pursuing further. So we looked at it, and we look back at our sort of initial idea of making it as simple as possible to use this, right, and to build an optimization and solve an optimization problem as simply as possible. And we quickly realized that, yeah, we're not really there yet. Okay, and one big problem is that, yes, you have your DSML and somebody can build that for you and you know how to use it, but now you want to do an optimization, so you need to write these graph transformation rules for it. And that, it turns out, can actually become really difficult, right? So if we just briefly look back at this rule from the refactoring case, writing this and making sure it's correct is a challenge already. Showing it to the person who's actually has the problem of doing this refactoring and convincing them that this does the right thing is yet another big problem. Okay, and so these things can become quite complicated quite quickly. And so the interesting question for us was, can we do something about this? Okay, and the nice thing, of course, is because graph transformations have a fairly strictly formalized structure and are effectively graphs or collections of graphs, if you wish, themselves, we can generate graph transformation rules. And the question then became, can we generate graph transformation rules that we can use as mutation operators in our search and that are at least as good as the operators that we would write manually? Okay. And so we looked at this and we tried to figure out, how can we go about this? And so we extended our MDEOptimiser tool so that now, instead of describing specifically the set of Henshin rules that we're going to use, we can just describe what part of the meta model should be up for change. Okay, so this example here is taken from a different case study. This is about trying to decide which features of an application should we focus on in which sprint of an agile sort of application development lifecycle. And there we have a meta model, and the key thing here obviously is we want to create those sprints, right? And so here we're saying there's lots of information in here about the features and the dependencies and whatever in our model, but the thing that we actually want to optimize is the set of sprints with their dependencies to everything else in our models. And so we just say that's the thing that we wanted to mutate. Go ahead and generate rules for us from that. And so here's the meta model to this, and this annotation that I've just shown you essentially says this green part here at the top, those are the things that we want to allow to modify. Everything else is essentially just context information for the problem. Okay. And here is a rule that one might write manually for creating a new sprint. Okay, and one looks at this and one goes, right, okay, a sprint always has to have at least one work item. So, the author of this rule has been sort of reasonably clever already, and they've said, okay, well, in that case, it's probably a good idea if when I create a sprint, I also attach it to a work item. And I'm just going to briefly stop here to make sure if you can't read this notation because you haven't perhaps come across Henshin for any reason, then please shout in the chat. Given sort of the nature of this seminar, I'm going to assume that people have seen Henshin before and can read these. But if that's not the case, then please, ask a question. I'll be happy to explain the notation. So this is our manually written rule, which essentially says, when we're creating a sprint, we're going to attach it to a work item. And we've actually even figured out that a work item must be in at most one sprint. So it's probably a good idea to also add a negative application condition here to say that work item that we're going to pick for our new sprint mustn't already be in another sprint. Okay, so that's good. The slight problem with this is once we've got every work item in a sprint, we can no longer create new sprints with this rule. But actually for the search, it might actually be useful to be able to try out. So what happens, if I've got 2 sprints and they contain half of the work items each, it could be useful for the search to be able to say, what happens if I introduce a new sprint and just steal a work item from somewhere else, right? But this rule can't do that. So the rule that the search gets stuck at that point, essentially. Okay. Our generation algorithm will actually produce different versions of these sort of repairs for this edit. So it'll say, I'm going to create a new sprint, but I'm also going to now have to do something to make sure that the constraints for that sprint are satisfied. And here are different ways in which I could do this. So the top one is essentially the same as the manual rule, except that it's realized that it doesn't need to care about the stakeholder information here. So we're leaving that out from the rule. The bottom rule is a different rule. This is a rule that says we're creating a sprint, but we're going to steal a work item from a different sprint. But of course, we can only do that if that other sprint still contains at least one other work item, because otherwise that sprint would suddenly be empty and that's forbidden. Okay. And so you can already see where that's sort of going, right? So we're constructing these operators that we call consistency preserving search operators, or as we've recently been told by one of the reviewers for the journal version of the paper, we should really call them multiplicity preserving search operators, because at this stage, the focus, the constraints that we preserve consistency for are really the multiplicity constraints in our meta model and not any of the other constraints yet. And the key is that these operators consist of an edit operation, so something that makes a change to the model, and an associated repair operation that makes sure that that change doesn't introduce any inconsistencies in the model. And then we can further sort of subdivide these things. We can say, well, edit operations can be either atomic, which means they make a single change in one single place in the model, so basically to one model element, or they can be compound, which means they make multiple changes at the same time. We're interested in atomic changes really because we want to apply this in the context of search, and there often it can be useful to be able to go sort of step by step and say, if I make this little change here, what does that do to the overall fitness? Repair operations can equally be atomic in the sense that they only repair one place, one constraint. But that's often not enough, because if we introduce a new object, a new model element, a new instance of a meta class, there may be multiple edges attached to it that have multiplicity constraints. We may need to deal with all of them. And that's what we call an iterative repair, which basically says we're going to apply the same sort of pattern of repair to all the outgoing edges of a model element that we're introducing. And then there's another form of repair, which is recursive repair, which is where we allow the repair itself to create new model elements or delete model elements as necessary. Whereas in iterative and atomic repair, we only allow the repair to change the linking between model elements, the edges between model elements. So we saw that in our second create sprint rule, that rule was allowed to steal the work item from another sprint, but it wasn't allowed to say create a new work item or to delete another sprint or something like that, right? Which would also be a possible repair. We could say, I'm going to steal the last work item from another sprint and I'm going to delete that sprint. Might also be a possible repair, but that's not the kind of repair that we're looking at. And the reason we're not looking at that is because that sort of recursive repair then means we've now made another edit to the model, and we've got to now also produce the repairs for that. And very quickly we get into a situation where the rule generation algorithm might not even terminate. And so we've left that out for the moment. So we're focusing on atomic edits and atomic and iterative repair operations. Although in this talk today, I'm going to just give you some examples of atomic repairs. In fact, iterative is essentially then just applying all combinations of the relevant atomic repairs to the same sort of model element when generating the rule. So here is the sort of general pattern, right, of two meta classes with some reference between them, and there's some multiplicities left and right. And based on this pattern, what we essentially do is we enumerate all the relevant possible combinations, and for each of those, determine what's the general pattern of rule that we need to generate if we want to create an A or if we want to delete an A. What are sort of the relevant multiplicity constraints that for which we need to generate different types of repairs? We sort of catalog the different types of repairs. That's very similar to what Timo Kehrer did in his search tool, which was generating edit operations as Henshin rules. The key difference is that tool doesn't deal with situations where there's sort of a closed lower bound multiplicities, because that's not a thing that's easily doable in the context of sort of edit operations, I guess, because it immediately requires adding new edit elements and so on. And so we explored in particular that part of the generation space in more detail and determined what are the repairs that we need for those. And so we create different types of rules for creating nodes, deleting nodes, and manipulating edges in various ways. And for these, we then create various types of repairs. And in particular, for creating and deleting nodes, we create these three types of repairs. The simplest one is always to basically add an application condition. So in the case of creating a node, that's a negative application condition where we can say we're creating a node, but we can only do that if we can satisfy its constraints. For deleting nodes, it's a positive application condition. We need to make sure that the other side still has enough things attached to it. If we take one of its relationships away, as it were, right? that's nice, but it's actually, in terms of the search, often not a particularly useful rule, because what it does is essentially prevent us from applying this operator if we can't repair things, right? It's basically just saying can't do this, which for a search isn't great, because it basically just means, well, you can't move forward with the search. So we also create other operators that actually try to repair things. And now there's a whole spectrum of things here that we could do, right? Basically, it's about finding other model elements somewhere in the model that we can link up to make up our multiplicity requirements. And now where we find those objects, that there's a lot of options here, and we could generate a whole range of rules. And that again isn't particularly useful, because if we have lots and lots of rules, the search becomes inefficient just in terms of just having to pick which rule to apply. So we limit ourselves to saying we take the both ends, as it were, of the spectrum, the single source repair and the multiple source repair, where we basically say either every object that we steal from the same other object, or every object that we steal from a different other object, basically. So let me show you some examples of those. So here, for this sort of generic meta model that has our A and B with this sort of edge between them, and these are the things that we can change, here are some examples of these sort of rules, right? So on the left-hand side, we've got a single source lower bound repair. So if we're creating a new A, we need to make sure that that has at least one B attached. So we need to find a B for it. Okay, and we find an existing B, and we need to remove that B somewhere else. In that case, we're removing that B somewhere else, and we need to make sure that that other A still has a B associated to it, right? And similarly over here, if we're deleting this appropriately named new A, obviously it's actually an existing A that we're deleting here. If we're deleting that, then obviously we're deleting its edges to all these other Bs that it might be linked up to. And then we need to make sure that these Bs now are attached to other As. And this is a multiple target repair, which basically says we're not going to reuse the same A here. We're going to try and find different As for each of these Bs. Okay. Now, of course, these rules might not always apply because we've made these particular choices about the repairs. And there may be, if we generated a sort of halfway house repair rule, it might apply in certain contexts, but that's a choice that we made in order to limit the set of rules that we're generating. So let me just show you, how that impacts search. And that, I think, was actually quite surprising to us, because we were hoping that it would do at least as good as the manual rules. But it actually turns out that often, not always, but often, it does even better than the manual rules. And so that was actually quite nice for us to see, that not only does it reduce the amount of effort on our side for not having to write the rules, not having to make sure that we write the rules correctly, etc., but it can also give us better search. Okay, so this on the top is a comparison for the sprint planning example that we've just looked at. And again, the sort of purplish greenish line is the generated rules, and the reddish lines are the manual rules, so that the rules that we'd sort of handwritten, and we'd had handwritten them well before we started even thinking about generating rules. So they are indeed a distinct set of rules. And you can see that for both of these example models here, we're well above the manual rules. Actually, for the CRA case, the situation is a little bit more differentiated. Again, here's the sort of cyanish rule line is the generated rules, and there you can say it varies a bit. In fact, it's actually as the models grow bigger, the differentiation becomes a little less clear, right? But we still tend to sort of outperform over time the manual rules. But at the very least, even for the sort of initial bits, we're sort of doing at least as well as the manual rules. So that was quite nice. Of course, it raises a question, right? So we've done multiplicities, well, that's great. But what about other constraints, right? I mean, that's where the real money is, right? Multiplicities is cool, but actually the other constraints is what makes the rules really complicated. And so we started thinking about this. When this is, where we're slowly edging into the future work section, I guess, of this, we started thinking about this, and we realized, well, before we can even think about this, we've got to actually understand what it means for a rule to improve or sustain the consistency of a model over time for these sort of complex constraints. And that led to some really interesting collaborations with Jens and Gabi and Daniel, I think, who all but Jens are on the call as well, where we sort of just explored, I think, what it actually means for a graph to be consistent in a little bit more detail. And we identified this new notion of sort of partial consistency of graphs, which is, you know, if we have a graph and we've got some graph constraints, particularly interesting is that this is particularly interesting for universal graph constraints rather than existential graph constraints. Can we differentiate more than the black and white situation of the graph is consistent with regard to these constraints, or the graph is not consistent with regard to these constraints? Can we sort of separate this out a little bit more? And it turns out we can. It turns out we can say, well, actually, we can count the number of places where the context graph of a universal graph constraint occurs. So that's what we call the number of relevant occurrences of this graph constraint. And then we can also count the number of those places where the graph constraint is or isn't, in this case, satisfied. So where the implication, if you wish, of the graph constraint doesn't exist, the extension doesn't exist, right? And so that gives us a consistency index for a graph which runs from, the way we've defined it here, from 0 to 1, where 0 means the graph is not consistent at all with regard to this constraint, and 1 means it's completely consistent, but the numbers in between give us sort of a spectrum of consistency, a scale or a graduation of consistency of this graph. And that's really nice, because it means we can then also define a new notion of a new type of rule, as it were, which is, it's not just a constraint preserving or a constraint guaranteeing rule. A rule can be consistency sustaining or consistency improving, in the sense that it maintains the level of consistency of our graph, or it improves the level of consistency of a graph without necessarily making the graph completely consistent. And that's useful in the context of search, again, for example, because there we don't necessarily need rules that fix all the constraints right away, but we certainly need rules that will eventually produce a graph that's consistent. This is something that I'm certainly very interested in exploring further. How can we, use these ideas to not only look at a given rule and judge whether it is consistency sustaining or improving, but generate these kinds of rules. And Jens has come up with some initial ideas there for generating essentially the sort of application conditions. But the interesting question, again, of course, is also to look at ways of generating other types of repairs that will make rules consistency improving or consistency sustaining without necessarily having to just block their application in certain cases. We're currently working on some interesting stuff in the context of feature configuration, which doesn't yet sort of use generalized constraints, but uses more complex constraints than just multiplicities, and that's really good fun and really promising. So hopefully we'll be able to write about this fairly soon. But the general, I think, direction would be really useful, because that would take us one step closer to that goal of being able to just say, this is the stuff that can change, this is the stuff that needs to be fixed, please go away and figure out what the rules should be for me. And even possibly at some point, we might be able to say, figure out what the refactoring rules should be automatically, which clearly at this point we can't do. Beyond that, I'm very interested in looking at ways of saying, do we have to do evolutionary search on that problem? Or can we, if you tell me this is the graph, the type graph, the meta model, and this is the subgraph that should change, can we automatically identify that this is actually an integer linear problem, or even a constraint solving problem, and we can just throw this, write up an encoding for such an engine and throw it at that engine and let that worry about it. There've been some interesting initial collaboration with people up in Glasgow, who are doing similar sorts of things, and which looks quite promising. But again, we need to watch that space. And obviously scalable search. So this is all nice, but if the moment we actually, as we're doing evolutionary search over models, if those models get bigger, we keep copying models all the time under the hood, obviously, and that's not particularly nice. I know we've got a talk coming up next time, I think, about graph programming, and I'm very much looking forward to that, because I'm very much hoping that that will help me understand some of the issues that we have with making our stuff scalable, which I believe those approaches have addressed some of those issues already. And that's me done. Thank you very much for listening, and many thanks to our collaborators. Again, they're all listed here, and some of them, I've seen Gabi and I've seen Daniel are on the call as well. Thank you very much. If you want to take a look at the tool, here is the website to the tool as well, and I hope the QR code also leads to that website. And that's me done.
Okay, excellent. Thank you very much, Steffen. So let me clap for everyone, since we cannot do that any other way. I have a few questions, so I have a list here, so I just start from the top and go through them, and if anyone else has a question, I can sort of, you can see them as well. So first question. So you said you had I mean, you made a choice basically to represent the modification operations, the mutation operations, directly using complex rules, and that obviously has the advantage that you're capturing the domain constraints much more precisely, in a sense, because you always guarantee that you produce meaningful models again, rather than sort of when you encode them into sort of bits, then maybe you don't have that. But obviously you pay because the operations themselves are more complex. So what is the effect of that on scalability? Is that possible to say?
Yes. So that can at times become painful. What I'm not sure about is where exactly the source of that is. So I guess there are two parts to this, right? One is I remember we've played at some point, experimented at some point with also doing things like crossover style things, where you have multiple models and you try and sort of take the best from both and take that out. And it turns out that quickly becomes very painful and very inefficient. So we gave up on that at some point, not least also because we got reasonably good results without it for the problems that we were looking at. But that's, there's an indication, I guess, in there that as your rules become more complex, the impact on performance of just executing those rules potentially becomes more problematic, right? We've seen that also in the sort of the feature configuration example that I've sort of mentioned briefly. We see sort of similar effects. What we've managed to do there is to then go and say, for this sort of problem, it's useful to think of the problem in this sort of world and terminology of graph transformations. But before you then actually run the search, you sort of translate it back into essentially bit flip type operations. But the operators that you generate in that way are still intelligent and domain specific, right? So they know that if you flip that bit, you must flip that other bit over here as well, because that's what we figured out when we generated the operators as graph transformations. But we don't actually execute them as graph transformations anymore, because that becomes prohibitively expensive at that point. But having that structure available allows us to think about the problem in a different way, and allows us therefore to generate operators that are more efficient.
Yeah, okay. I mean, I guess it also depends on the quality of the encoding into the bit.
So that's always a problem. Yeah, absolutely. So that's always a problem. So we did some work very early on when we started with this. I did had some discussions with Lawrence Mando in Malaga, and I before that I'd done some work with people over in York who'd worked on the CREP tool, which essentially does a sort of bit vectorish generic encoding, generic genetic encoding of models. And one of the key problems that we found there was exactly that you have this locality issue and you can do it if you sort of do a very problem specific encoding, right? If you sort of carefully design your encoding for a particular problem, then it's easy, well, comparatively easy to come up with an encoding that works. But if you want to have a generic way of being able to just give me your model and your DSML and I'm going to do a search on it, you want to have a generic encoding over that, it becomes really difficult to do that efficiently. And the big problem is you use locality. So you get these sort of situations where you flip one part in the vector and the complete model that this gene describes changes. It changes essentially almost unrecognizably from the one that you had before because the way you interpret the vector, right? And often it just breaks all kinds of constraints, and you've then got to repair things, and it becomes really painful. We did some work there that showed that you can do some repair, and it makes it better. But I'm not sure it's the way to go. So.
Okay, cool. I think Nicholas has a question.
Yes, thanks a lot for the talk. I had a question about, because I'm really not familiar with model transformations, but I'm quite interested in what are your objective functions, because I have a feeling, depending on what choice you have, some of them might be expressible, again, in terms of graphical writing. So, I mean, for example, if you should be counting certain patterns in your graph before and after applying your transformation, I could imagine there's some stuff one can do with static analysis just on the, the interaction of the pattern count with the actual transformation rules. But you seem to be saying more that you sort of get these abstract measures in terms of bit vectors. Could you maybe comment?
So, in principle, the beauty of a search-based approach to optimization, rather than sort of a constraint-solving type approach, is that anything that takes a model and produces a number is a good objective function for us, right? By and large, not all of them will necessarily lead to a really good search, because some of them will construct sort of a fitness landscape where our search just gets stuck with the operators you give it. But we can deal with it, right? There's no, in principle, there's no fitness function that we can't do anything with.
Are you saying that it's an input of the user normally, which fitness function to choose?
Yes. No, but well, I mean, absolutely. So the fitness function is if you are interested in finding an optimal model, so you need to tell me what it means for a model to be optimal, right? So and the fitness function is what you use to do that. But if you go into constraint solvers, because the way they handle those sort of functions to try and guide their search, they sort of want to be able to analyze the functions, and that isn't always possible for some functions, right? So we can basically take any arbitrary Java code, so you can literally run a simulation on the other end if you wanted to, or I think we have one example where we actually generate the fitness function generates out a file-based representation of the current solution, sends that to a separate tool that sort of reads in that file, does an analysis based on AI planning, comes back with a number, and it's terribly slow. Don't get me wrong, right? It's not something it's not the sort of search approach where you get, in that case, where you go, let's press the button and a few seconds later you get a result. But you can do it, and you can fit it into the search. Now,
but you don't have sort of a.
We've used
you don't have like a very direct feeling whether constructing your fitness function based upon graphical pattern count rules will actually lead to an improvement, because I mean it sounds like you're not really using much of this concurrency type theorem computations of
no, we don't use that. we have one bit of work where we do it, where we use a little bit of critical pair analysis, but I haven't really talked much about this. I'm happy to talk about this a little bit more, but that's so at the moment in terms of what it gives us. Using graphical patterns for describing the fitness functions could be interesting in terms of making them more intuitive, right? So we essentially already allow you to write an OCL query that queries the model and gives us a number if it's literally just about the information in the model. And in many ways, you know, the idea of using graph patterns for that is to me at least is similar to that. It's just using a different type of query language in that sense. But we wouldn't, you know, do any analysis over that in order, at least at this point, in order to improve the search. When we come back to this idea of possibly translating to other solvers, rather than doing a search base, then that becomes potentially relevant, right? Because there you may want to be able to analyze your fitness function and say, oh, that's the sort of fitness function that I know that this type of solving approach can actually deal with. Mm. And then that might become more relevant.
Thank you.
Okay, very good. Thanks. Arthur has a question. Arthur, do you want to ask that in audio?
Yeah, that's fine. That's fine. Sorry, I don't have the camera on. So very nice talk, Steffen. Thank you very much. And my question is about the use of your approach and your tool for generating test suites, for example, where the fitness function doesn't characterize a consistency state. The main goal would be here to break that consistency in order to define a number of interesting data fixtures that you can use in a test suite. And the question is, have you used MDEO, your tool, for generating test suites? And if not, do you think it could be used for it?
So we haven't done it. It's possible that it could be used for that. Although I suspect that things like the Lane's tool or Daniel's graph solver tool might be a tad more efficient at that sort of thing, where it's about saying, it's basically going, you have nothing, you have a meta model and nothing else, generate me some instances that satisfy some constraints effectively, or you know, don't satisfy constraints, which is sort of a negation of the above, right? And that's what these tools are really geared to. And so they might end up, they're probably going to be more efficient at doing that, but we haven't tried it.
I see. But here, the fact that you have a fitness function and that you can actually use it to perhaps add count or to add some level of uncertainty about the different constraints that can be detected, perhaps your approach could actually generate test suites that are more interesting. But
possibly.
I'm just brainstorming here. I'm not.
Yeah, I think it's an interesting idea. We've never really thought about it because the fitness functions, they're sort of a bit more soft than a constraint in a way, right? Because they're not sort of black and white, and so because constraints are a bit more black and white, it becomes, you know, you can do other things in your search there as well, right? And I think that's sort of what is correct me, Alexandru, is Daniel's tool, is it called Graph Solver? I think it is, isn't it? And or Lane's Autographer, I think they sort of do these sort of things, right? Of basically generating instances that fit with particular constraints and giving you diversity over that and things like that. But it could be interesting to explore, absolutely. And I'd certainly be happy to chat about that more.
Thank you.
Okay, very good. Thanks, Arthur. Gabi has a question as well.
Yes. Actually, a small question. In the beginning, you said the general search space for an optimization problem is defined by DSML. And considering, for the example, the CRR case, you have class diagrams as DSML. And the problem model is not yet a class model because there are no classes. Yeah. So do you consider several different DSMLs for problem models and solution models? And
we cheat. So the question is absolutely relevant. I haven't talked about problem and solution models much, but that is an important distinction, because typically in these problems you'll have not typically, often in these problems you have this situation where you're given a model which, strictly speaking, isn't a valid instance yet of your solution meta model, because it's missing things that at the point of the whole search is to find these missing things and fill in these missing things, right? And in the CRA case, you've rightly pointed out that there you're typically given a set of methods and attributes and dependencies between those, and the job is to sort them into classes, but there are no classes yet initially, right? However, the meta model actually demands that every feature, so every method and every attribute, be in a class. And so, strictly speaking, the problem model that you're given isn't actually an instance of that meta model. And so what we do is we ask to be given the meta model for the problem. So with the constraints for the problem, and then we ask to be given an indication of which constraints are strengthened in the solution meta model. So we don't do two separate meta models. We just allow the constraints to be changed. So for the CRA case, you would basically give us a meta model that already has a notion of class in it, but doesn't require that every feature be contained in a class. And you give us an additional constraint that says, but for solutions, every feature must be contained in the class. And what that allows us to do is actually, when we generate the rules, we actually generate two sets of rules. We generate a set of rules for the problem meta model, so a set of rules that will just work on those, and we generate a set of rules for the solution meta model, so for the one that has those additional strengthened constraints, and will work in that context still. And then we basically take the union of those rules, because some rules will occur in both sets, and we obviously don't use them twice, and that's the set of rules that we then take forward, basically.
Mm-hmm. Okay, thanks.
Okay, thank you very much. So I mean, I had a couple of minor questions, but I suggest that unless there's any other question from the audience, we close the official part here and sort of take the rest in a sort of smaller private context. Yeah.
Private meeting, we stay online, of course.
Yeah.
We have to stay online, yes.
So we stay online, but we close the YouTube channel and discuss the rest sort of between us. So thanks very much again for the talk and for the questions, everyone, and for answering the questions, obviously, Stefan. And we switch off the YouTube then. Okay. Thanks. So if I can just continue, I sort of maybe just go through my list to see what else is there that is worth discussing. So I was wondering about